Welcome to clickmyproject.com. Our product title is Timing Error Tolerance in Small Core Design for SOC Applications. Next we see about abstract of our product. Generally VLSI technology is to optimize the any type of digital architecture because this type of optimization process is mainly used to enhance the various applications. The proposed design approach provides timing error tolerance at the small banality of one clock cycle delay. In the circuit operation, for each error correction, the main objective is to develop a low-cost multiple timing error detection and correction techniques, which is based on a new flip-flop design. In addition, it is characteristics by very low silicon area requirements compared to previous design schemes. This design based on a new flip-flop design, that is edge-triggered T-type flip-flop. In this process, each bit in a data is processed through a pipeline stages. This work presents a reliability aware design technique which provides low power and cost efficient timing error tolerance in nanometer technology. Small core designs that are the building blocks for many core system on chip applications. This design is carried out by CMOS technology in Tanner EDA tool. Next we see about flow diagram of our product. This is our flow diagram. First of all, the input data is given to the edge trigger T-type flip-flop, and that D flip-flop consists two parts and two XOR gates and one is latch. At the positive gating edges is used in this edge triggered T-type flip-flop. The clock pulses is given to the D-type flip-flop. The Q will assume the same level as input of D unless either asynchronous input gets control. A logic 0 on the asynchronous input S at any time will cause Q to be set to logic 1 from the time S goes low until the first clock pulses after S returns to logic 1. A logic 0 on the asynchronous input OR will cause Q to be reset to logic 0 from the time OR goes low until the first clock pulse after OR returns to logic 1. The action of the asynchronous input overrides any effect of the D input. Both asynchronous inputs should not be low at the same time as both Q and Q bar will be at logic 1. This is a non-allowed state. After the processing of edge trigger T flip-flop, that is fed into the error T flip-flop and release unit. In this unit, the error is detected and corrected by using of error T flip-flop and release unit. It consists pulse generator, XOR gates and gate arrangements and register. The first XOR gate detects the difference and raises its output compared to high. The latch captures and alters this response. Thus the second XOR gate provides at its output Q the complement, and now the Q output of the EDC flip-flop carries the correct value which feeds the subsequent logic stage for its computations. Consequently, the error is locally corrected. After that, that process is fed into the latch. The T latch or transparent latch is a simple extension of the gated SR latch that removes the possibility of invalid input states. Since the gated SR latch allows us to latch the output without using the S or OR inputs, we can remove one of the inputs by driving both the set and reset inputs with a complementary driver. We remove one input and automatically make it its inverse of remaining input. The T latch output the D input whenever the enable line is high, otherwise the output is whatever the D input was when the enable input was lost high. This is why it is also known as transparent latch. When enable is asserted, the latch is said to be a transparent. Its signal propagated directly through it. Next we see about running process of our product. In our product is done in the Tanner EDA tool. The Tanner EDA tool is a CMOS technology design tool. First we open the SEdit window. Now the window will be open, then select the file and create a new design. Now after the creating the new design, we select the cells. In the cell, various views are here, so we select a corresponding view, and after that the whatever we record designed elements in this window, the various kinds of elements are showing here. So whatever we record, that elements is taken to the cells. After connecting the elements as per the circuit diagram, we save the file and select the corresponding library tools. After that, click the start simulation icon, then that window will be starts to run, and corresponding output window will be open, and also the corresponding timing window will be open. The first one is the timing window. This is a time summary, whatever we used in this architecture, how much time is taken to simulate the architecture. This is our record time, that is 22.52 seconds. And the next one is the output window. In the output window, this is the input voltage levels and output corresponding output voltage levels. This is the output power. In our product, the output power consumption is around 900 microwatts. That means 0.9, not 9 watts. So the overall power consumption is very low compared to the other CMOS technology designs and also other VLSI designs.